is a review of things you already know from Algebra 2. I want to get to those examples where we can talk about some of the detailed parts about domain and range and how to do the rational function inverse. This is the last set of notes for Chapter 1. Your test is on Wednesday. Tomorrow is going to be a review for you. You should be familiar with this notation where you have it looks like a -1 exponent, but it doesn't really mean anything. Like mathematically, you don't do anything with the -1. It's just telling you it's an inverse. And you guys know that inverses are switching x and y. I think this is a great thing for a pre-calculus student to make note of that we didn't really spend a ton of time with in Algebra 2. We really focused on the whole switch x and y part, and now we're going to say, well, we know to switch x and y, let's now be thinking about domain and range. If your domain was all your x's and your range was all your y's, and then you flip them, the domain and the range switch. So that's a nice way for you to check your final answer's domain and range. Is it swapped from the originals? And then down at the bottom, I just have a simple statement about verifying inverses. I wrote it as f of g of x and g of f of x, but of course you could replace that g with the f inverse if you wanted to. So if you do the composition f of f inverse and f inverse of f, it should always come out to equal x. Okay. So inverse means opposite in math. You're performing the opposite operation when you do the inverse. If you do a composition of two inverse functions, they'll undo all the numbers, and the only thing that'll be left over is 1x. And it has to work both ways, and then they are inverses of each other. You should have also discussed in Algebra 2 that when you look at graphs of inverses, and this will be helpful for us when we're thinking about some of the stuff we're doing in pre-calculus with the inverses. The graph of an inverse is the reflection of the original in the line y equals x. It should make sense that the reflection happens in the line y equals x, because when you switch x and y in the equation, you're basically saying they are the same thing if you make substitutions for each. The line y equals x is the linear function, like the identity function that passes through the origin with the slope of the line. Now, I'm going to turn off the lights so you can see the images better. I don't know that you necessarily have to draw these in your notebook, but I just want to bring to attention something that we're going to be discussing here momentarily so you can have a visual of what's happening. So I'm going to start with this image. I just pulled it from the internet. I asked for an inverse of a quadratic function. Okay. So the blue graph is y equals x squared, just a regular parent graph for a parabola. I've got the dotted green line, which is the line y equals x. And can you see visually that the red graph is just the reflection of the blue graph over the line y equals x? Okay. What's interesting about this picture that I want you to be thinking about as a pre-calculus student is that the blue graph passes the vertical line test, meaning it is a function, but the red graph doesn't. Okay? So I'm going to make a little note here. This is an example where the inverse is not a function. The inverse is not a function. In pre-calculus, our textbook is only concerned with inverse functions. So if you come across a problem where you could recognize the inverse would not be a function, don't have to do it, because we don't want it, unless it's a function. Now, I could adjust this graph, this blue graph, right? If I didn't have both arms of the parabola, I could reflect one arm and the inverse would be a function. So this is a modified graph where we can find an inverse function for a quadratic. Okay. But the domain has changed. So this is y equals, I'll write it bigger so you can see it, y equals x squared, such that x is greater than or equal to 0. I'm cutting my graph into a smaller piece where if I reflect this arm of the parabola over the line y equals x, then the inverse is a function. So these are things that you're going to be thinking about as we progress through this section. Reminder, our textbook is only concerned with inverse functions. If you realize it's not going to be a function, you don't have to find it. Okay. You may see the textbook use notations like this for domain, where x is greater than or equal to 0. You recognize that that statement is there so that you can find an inverse function. Okay, it doesn't really mean anything other than just use this part of the graph. Okay, so last thing before we get into our examples. There's two other things that we need to be aware of, and this goes back to this idea that our textbook is only concerned with the inverse functions, which means we're basically looking for something called a one-to-one function. Now, a one-to-one function is a special kind of function. So it's already a function. If it's already a function, remember that means every x has only one y. Every input has only one output. Okay. If it's a special kind of function that's called one-to-one, it also means every y has only one x, which is not always true for all functions. If a function is one-to-one, it has an inverse function. Okay? If every x has only one y and every y has only one x, you'll be able to find an inverse function. There's a check for this. How can you tell if a function is one-to-one? Well, of course it has to pass the vertical line test, so it is a function. But to see if it's one-to-one, perform a horizontal line test. So you're looking at the original function. If every horizontal line intersects the graph at exactly 1 point, no more, then f has an inverse function. It's one-to-one, there is an inverse. So what I would recommend, how are we going to use this knowledge about one-to-one and horizontal line test is, before you start a problem where you switch x and y and solve for y to find the inverse, make sure there is an inverse function first. So just think about the graph. Does it pass the horizontal line test? If it does, continue. If it doesn't, say no inverse function and move on. Okay, so now that we have these two bits of information, we're going to jump into some of our examples, and I'll talk about how to use the one-to-one and the horizontal line test. Okay. I'm going to start with the one on the left. F of x equals the square root of x plus 1. Now I do have up at the top that we're going to be focused on domain and range, right? That's been a big part of our class so far. A little bit more than we were in Algebra 2. So the book is going to be giving you a problem like this, an equation, and it's going to ask you to find the inverse function. Before you go about finding the inverse function, I would verify that 1 exists. That should be pretty easy. Some of you will draw this out, and some of you can just think about it in your head. Think about function yoga from Friday. If I put this on the board in function yoga, think about the parent graph, the one arm, right? And it's going left 1. Okay? So whether or not you draw that out is totally up to you, but you need to be able to picture that in your head so that you can run a horizontal line test. Does that function pass the horizontal line test? Yes. So there is an inverse function. I should keep working. How do I find an inverse? Switch x and y. Let's do it. X equals the square root of y plus 1. Solve for y. What should we do first? It is being square rooted, so we're going to do the opposite, which is square both sides. So I get x squared equals y plus 1. Then subtract 1 from both sides. I'm going to flip-flop this around. Y equals x squared minus 1. And if you want to say f inverse, you could also do that. So I'll add that in the front. F inverse of x equals y equals x squared minus 1. I'm not too picky whether you use y or the f inverse. I'll accept either one. Okay, now stop and think about that. If I put x squared minus 1 on the board in function yoga, what would you do? Parabola? Down 1? Okay. Will this graph, when reflected in the line y equals x, give me a parabola? No. It will only give me one arm of a parabola, right? So that means if the graphs don't match, this is like number 3 on the green sheet. I have to address that. I have to say, don't do the whole parabola. Do the one side of the parabola. Now, there's a couple of different ways you could go about doing this. If you've got this image in your head, the starting point for that square root function is at -1, 0. If you switch x and y, that point is now going to be at 0, -1. So the first x that works is 0. And then we're going to see the graph of the right side of the parabola. So we could say x greater than or equal to 0. You just want the one arm of the parabola. We're just reflecting one arm, square root. Without this statement, x greater than or equal to 0, your answer is wrong. Because your answer would be a whole parabola, and a square root won't make a whole parabola. It'll only make half of a parabola. So that's like number 3 on the green sheet. Another way for you to have found that x was greater than or equal to 0 is if you thought about domain and range. So remember, I had said up on the top of the screen earlier that we should state domain and range. Okay. Domain and range of the inverse are switched from domain and range of the original. So if you can imagine this original square root graph, I'll put it in red right here, that original square root graph, you should be able to name domain and range for that. Domain started at (-1) with a bracket, right, to positive infinity to the right. And the range started at 0 because there was no up and down movement in our transformation. So 0 to infinity. And if you flip-flop those, domain should be 0 to infinity, which would give you this x greater than or equal to 0. So if you're not sure where your x starts, go back to your parent graph and do domain and range, and then the domain will be the statement that you need. So I'm just going to flip-flop those. What is this? 0 to infinity and (-1) to infinity. Okay. Yes, Lexi. On the quiz or the test, it's going to ask you for, it'll have a spot for the inverse function, which I need you to write out the function, and in this case you need the restriction behind it, so we get the one arm. And then it will have a spot for domain and range to the inverse. It would be totally up to you if up in your work you did domain and range of the original. I think it's really easy to do domain and range of my original and then flip-flop them, but it's totally up to you how you want to go about doing it. Good question. Anything else that you want to ask about on that one? Okay, you have to worry about this whole issue, right, with the domain and that little restriction piece whenever you're going from an even root to a function that is an even power. So if you had a square root to a quadratic, a fourth root to something raised to the fourth, those are the times when you have to be concerned with restricting your domain. Would I have to worry about that with odd roots? No, because they don't look like U's. Okay, they'll be that whole graph, and that whole graph is like that sort of like S-shaped graph. Okay, let's look at f of x equals the quantity x plus 1 squared. Think about function yoga. You should be able to picture this in your mind. This is what parent graph? Parabola, and it's moved in what direction? Left 1. So in my mind, I'm picturing a parabola, moved left 1. Does this pass the horizontal line test? Nope. No inverse function. The book is asking you in the direction for inverse functions. If there isn't an inverse function that is not one-to-one, it does not pass the horizontal line test, there is not an inverse function. Moving on. Okay. Now, if the book gave you this problem, f of x equals x plus 1 quantity squared, and then put some kind of restriction behind it for all x is greater than or equal to (-1. Think about that one. That would be just one arm of the parabola. Would you have found the inverse then? Yeah. What kind of function will your inverse be? A square root function. You'll switch x and y, you'll have to square root both sides, you'll subtract the 1, it'll be a square root function moved down 1. Okay. Let's do one of those rationals. So I'm going to do the one on the left. We may or may not do the cubic function. Cubic function isn't too bad. You've done those in Algebra 2, no problem. Okay, get that rational function down. Now, on your homework, on the test, if we ask you to do inverse of rational functions, they're going to be what I would call simple rational functions. So the rational function on your 8 basic function sheet it's called the reciprocal function. And when you drew that parent graph, it looks something like this. Do you remember that on the 8 basic function sheet? So if I am giving you a rational function, one that looks like a fraction in chapter 1, it's going to pass the horizontal line test. Some issues that you might recall from Algebra 2 or Algebra 3 is that there are asymptotes in that picture. There's a vertical asymptote and a horizontal asymptote. So those cause restrictions to your domain and restrictions to your range. Okay, and so that's something that we're going to address at the end when we state domain and range. But we'll focus right now on saying it passed the horizontal line test, let's find the inverse. So what do we do first? Switch x and y. I'm hoping that on the green sheet for number 4, everybody at least switch x and y. Okay. After you switch x and y, your goal is to solve for y. Did any groups talk about what they might do to solve for the y? Yeah, I like that idea. You're going to be troubled by solving for a variable that's in a denominator, right? You don't really solve for x's or y's in denominators. You get them out of the denominator. So Lexi is saying multiply both sides by y plus 2. I love that. Let's do it. If I multiply the right side by y plus 2 and the left side by y plus 2, the y plus 2's cancel out. On this side, I could do what? Distribute that x. So I would always go ahead and distribute. If you don't distribute the x, there's really like nothing else to do. So you've got to distribute the x. So we're going to get xy plus 2x equals 5 minus y. Okay. Now again, reset your goal. We are trying to solve for y's. When we multiplied both sides by y plus 2, like Lexi told us, and we distributed, we now have y on the left and we have y on the right. You can't solve for a variable when it's on different sides of an equation, right? So I'm going to make a note here. Get y's on the same side. This is where a lot of people are going to get stuck. They're like, okay, well now what do I do? Okay, you have to reset the goal of solving for y. You need the y's to be on the same side. If a term doesn't have y, get it on the other side. So I'm probably going to add this y over, call it xy plus y. And then this 2x doesn't have a y, so I'm going to move it to the other side. Call it 5 minus 2x. Is everybody okay with my rearranging? Let me know if you have a question. Why did I rearrange? Because if I'm solving for a variable, I need it to be on the same side of the equal sign. Okay. Now, we have two y's, but we can't really add these together, right? An xy and a y are not like terms. But if two terms are being added together and they both have y in them, you can factor out the y. So now I'm going to write a little note to myself. I'm going to factor out y. You should have only terms with y's on them in the left. So you can take a y out of everything. That leaves me with x plus 1. Don't have to worry about the right side. There's no y's over there. We'll just leave it as 5 minus 2x. Can you get y all by itself? Divide by x plus 1. So y equals 5 minus 2x over x plus 1. The inverse to a rational function is another rational function. Okay. Questions about our process? If you are going to look back at your notes and this algebra in black isn't going to make any sense to you, you need to write these statements in your notebook so you know why you're doing the things you're doing. You're getting y's on one side, and you are factoring out y. And in a rational function, it will always be the same way, because you'll always have a mix of terms with y and terms without y's. Okay, let's do domain and range. Here's how I would recommend you do domain and range for rational function in chapter 1. We are going to do rational functions more in depth in chapter 2. But here's what I would focus on. Remember way back earlier when we talked about like the things that you can't do in math? And one of them is you can't divide by 0. So the rational functions are always creating issues for us. If this is my inverse and I'm thinking about domain, there is a number that I can't put in for x. What can I not put in for x in this inverse? -1. Can't do it. So that's going to be my domain. -infinity to -1 in union with -1 to infinity. Include everything except -1. Okay, now range, what I would do is I would use my information about inverses. The range of my inverse is the same as the domain of my original. So if I scroll back up to my original, the original was also a rational function, which looks like a fraction, and I still can't divide by 0. So what x doesn't work in the original? -2. So this domain was -infinity to -2 in union with -2 to infinity, which is the range of my inverse function. So I'm going to say that's the range of my inverse. So I'm going to take that and go here, -infinity to -2 in union with -2 to infinity. Right? And make sure you know how to write interval notation for skipping a number, right? Okay, now, side note, if you care, because we're going to do it in chapter 2 anyway. The range is affected by the horizontal asymptote of a rational function. The domain is affected by the vertical asymptote. The vertical asymptote is setting your denominator equal to 0. So, of course, we get that when we do domain. For the horizontal asymptote, there were 3 rules that we'll review in chapter 2. But what we have here is in the numerator, we have a linear function. In the denominator, we have a linear function, so they have the same degree. When the degrees of the numerator and the denominator are the same, your horizontal asymptote was the ratio of their leading coefficients. So -2/1 or -2. Y equals -2 would have been our horizontal asymptote. Notice, what did we exclude in the range? -2. So if you remember that piece about the horizontal asymptote, that would work for a rational function. Do you agree that this domain is the range of our original function? Exclude -1. If I scroll back up to the top, if you were to do the horizontal asymptote for the original function, you would look at the leading coefficient to these x's, which is -1/1, and you would exclude -1 from the range. So the horizontal asymptote is agreeing with the domain and ranges that we have. Okay, but I would say most of you probably would be fine with just looking at domains. Okay, any last questions? We've got about 15 minutes. I want you to pull out that green sheet. And if you didn't finish number 4 with your group, see if you guys can do that. I'll go back to the slide that has the answer to number 4 and see if you can do that whole get y's on one side, factor out y. And then you guys can also check to make sure that I typed that correctly on here. It is, I have -x over x minus 1. See if you can get that. I'm going to hand back your first set of quiz corrections, and then I'm going to hand back your new quiz from Friday.